In previous lessons over differential equations, you've actually solved exponential growth differential equations to get a solution such as some constant, the initial amount, times e to the kt. If k is greater than 0, you have exponential growth, but if k is less than 0, you have exponential decay. Exponential growth covers lots of things that happen in real life, like the growth of bacteria, or the growth of money in a bank account, or the growth of a population. But in reality, consistent exponential population growth is not sustainable. That's where logistic growth models come in. A logistic growth differential equation can show up in many different forms. The form we're going to look at most closely today is Kp times m minus p, where m is the carrying capacity or the maximum. Our solution for that is m over 1 plus c e to the negative kmt. Unlike in the exponential growth equation, c is not the initial amount. The inflection point for logistic growth occurs at half of the carrying capacity, when y is m over 2. It also represents the time of most rapid growth, where the slope is steepest. For our example, a national park is capable of supporting no more than 100 grizzly bears. We model this equation with a logistic differential equation where k is equal to 0.001. For part A, write the differential equation. P represents our population, and our carrying capacity, or our maximum, is 100 grizzly bears. So m would be 100. Go ahead and plug in dp over dt is equal to k, which is 0.001, p, our population variable, times 100 minus p. The slope field for this differential equation is shown. Where does there appear to be a horizontal asymptote? It looks like y equals 100. What happens if the starting point is above this asymptote? The population of bears will decrease. What happens if the starting point is below this asymptote? The population will increase. If the park begins with 10 bears, sketch a graph of p of t on the slope field. Starting with 10 bears is an initial point of 0, 10, and follow the slopes to get an estimate of your solution curve. Solve the differential equation to find p of t with this initial condition. To separate our variables, I'm going to multiply both sides by dt and divide both sides by p times 100 minus p. I'm just going to leave the 0.001 on this right side. Now that our variables are separated, we can integrate both sides. The integrand on the right, I could distribute in p. Even if we distribute p, you'll notice that you won't get something simple like u prime over u or arctan. And the best way to simplify this integrand is to do it with partial fraction decomposition. To solve for a and b, we'll plug in 100 for p and 0 for p. Now we can split this integral into two fractions, a over p plus b over 100 minus p. Before integrating, I can even factor out a 1 over 100 on the left side. The integral of 0.001 with respect to t is 0.001t plus c. I can multiply both sides by 100 to get this 1 over 100 to the right side. When you distribute 100 times 0.001t, you get 0.1t. When you distribute 100 to a constant, you get 100 times a constant, which is another constant, so it remains as c. The integral of 1 over p is natural log absolute value p. This second integral is also almost u prime over u. U prime would be -1, so I need to multiply -1 times -1. Natural log absolute value, 100 minus p. In order to solve an equation with multiple natural logs, we need to condense these logs first. The difference of two natural logs is the same as the natural log of their quotient. To undo natural log, we exponentiate both sides to have the base of e. E to the power of anything cannot be negative, so at this point we can remove our absolute value. Remember that if you have e to the power of a sum using properties of exponents, you can change that to a product with the base of e. E to the c is also a constant, so we turn that into c and it becomes the coefficient of e. To get p by itself, I can multiply both sides by 100 minus p, do some distributing, do some division, properties of exponents, and then get all the p's to one side. To save a little time, I'm going to flip both sides of this ratio. 100 minus p over p is equal to 1 over ce to the 0.1t, or ce to the negative 0.1t. You may be confused as to why I did it that way, but it will become clear as we continue. Multiply both sides by p, and then add p to both sides. Factor out p, and solve. Oh my goodness, we got a general solution, and now we're going to solve for our particular solution, the one that goes through 0, 10. Plug in 10 for p, 0 for t, and solve for c. We'll multiply both sides by 1 plus c. And you get c equals 9. So our particular solution, we'll call that p of t, is equal to 100 over 1 plus c e to the negative 0.1 t. Wow, wasn't that fun? Instead of solving the differential equation, use the general form of a logistic equation or our solution form to find the same solution. Plug it in. Hey, that's what we got for our general solution from part D, and then plugging in your initial condition of 0, 10 would yield c equals 9, and so from there you would get the same particular solution that we did in part D. You may wonder why we even solved it all if you can just memorize the solution form, but sometimes the differential equation is not in kp times m minus p form, and so it's hard to tell what k and m are, so it may be hard to plug into the solution formula. And of course, if you forgot the formula, you'd have to solve by separation of variables anyways. Find the limit of p of t as t approaches infinity. No matter where your initial value is, whether it's below or above our horizontal asymptote, as t approaches infinity, your population will approach 100. When will the bare population reach 50? To solve part G, we're going to take our particular solution and plug in 50 for the population and solve for t. First, I'll multiply both sides by this denominator. And then divide both sides by 50. The inverse operation of e is ln. Take the natural log of both sides. Multiply both sides by -10 to isolate t. Using a calculator, t is equal to 21.972 ... So when will the bear population reach 50? After approximately 22 days. When is the bear population growing the fastest? Logistic growth population is the fastest at its inflection point, where the y value is m divided by 2. Our maximum or carrying capacity is 100, so m divided by 2 is 50. Oh hey, when will the population be 50? We already solved that. At t equals 21.9 blah blah blah. When is the bear population growing fastest? On day 22, or on the 22nd day.